Right now, as you read this, our galaxy contains somewhere between 200 and 400 billion stars. Not 200 billion in the way a government budget uses that number as an abstraction, a figure too large to feel real. 200 billion individual suns, each one a nuclear furnace burning through hydrogen at a scale that makes the largest human engineering projects look like children drawing in sand. Some of these stars are young, still wrapped in the gas clouds that birthed them, their light not yet escaped into open space. Some are old beyond comprehension, burning with a patience that stretches back to eras when the universe itself was still learning what it wanted to be. Some are enormous red supergiants, so swollen that if placed where our sun sits, their outer atmosphere would swallow the orbit of Mars. Some are small and careful, red dwarfs burning so slowly they will still be shining long after the universe has grown cold and dark. And among all of them, somewhere in that vast turning machine of stellar fire, stars are dying. Not metaphorically, not eventually, now. At this moment, while you breathe, while the night outside your window holds its familiar shape, massive stars somewhere in the Milky Way are approaching the ends of lives measured in millions of years. Their cores are running out of fuel, their internal balance is shifting. Gravity, which has been pressing inward since the moment each star was born, is finally beginning to win. At some point, perhaps tonight, perhaps 1,000 years from now, perhaps yesterday on a cosmic clock, one of them will cross a threshold. The core will collapse. Matter will compress beyond any density you can visualize. A shockwave will tear outward through layers of gas and plasma. And for a few weeks, one dying star will release more energy than our sun will produce across its entire 10 billion year lifetime. That is what a supernova is. That is what should be happening in our galaxy by all reasonable estimates several times per century. So why haven't we seen one? Not in your lifetime, not in your parents' lifetime, not in your grandparents' lifetime, nor in any lifetime, stretching back 4 full centuries. The last time a supernova blazed in the Milky Way bright enough for the naked human eye to catch it, bright enough to stop someone in their tracks and say, "There, that was not there." Yesterday was in the year 1604. Johannes Kepler was alive. Galileo was alive. The telescope had not yet been invented. Shakespeare was still writing plays. And overhead, a star exploded, burned brilliantly for months, and then faded. Since then, silence. 400 years of astronomy growing more sophisticated by the decade. 400 years of telescopes, spectroscopy, radio waves, infrared imaging, space-based observatories, automated sky surveys, scanning millions of objects every clear night. 400 years of astronomers building instruments of almost unimaginable sensitivity, detectors buried deep underground to catch particles that pass through entire planets as though they were made of fog. 400 years of watching, and in our own galaxy the quiet has held. That silence is the question that will carry us through tonight. But here is what almost everyone gets wrong when they first hear this. The absence of a visible supernova in 4 centuries does not mean the Milky Way has stopped producing them. It does not mean stellar evolution has paused. It does not mean something is broken or wrong, or that we are living in a statistically cursed era. The real answer is stranger, more layered, and in many ways more beautiful than a simple nothing happened. Because the truth is that something very likely has happened, possibly more than once, and the galaxy simply declined to show us clearly. The Milky Way is hiding things from us. It has always hidden things from us, and tonight we are going to learn why. If you find this kind of journey worthwhile, the slow, careful kind that takes a familiar question and turns it over until its real shape appears, do me a small favor and hit the like button and subscribe. It genuinely helps this channel reach other people who find themselves looking up at night and wondering. Now get comfortable. Let the quiet settle around you. We have a long way to go, and the distance is worth it. Let's begin. To understand why we haven't seen a recent supernova in the Milky Way, we first need to understand where we are standing when we look, because the view from inside a galaxy is nothing like the view from outside one. And that difference, that simple accident of our position, explains more of the mystery than almost anything else. Our galaxy, the Milky Way, is a barred spiral galaxy. That description alone carries enormous weight. It is roughly 100,000 light-years across from one edge to the other. Let that number sit for a moment. 1 light year is the distance light travels in an entire year, moving at approximately 186,000 miles per second. In 1 year, a beam of light covers nearly 6 trillion miles. The Milky Way is 100,000 of those years wide. If you somehow built a spacecraft capable of traveling at the speed of light and pointed it toward the far edge of our galaxy, your great-great-great-grandchildren's great-great-great-grandchildren would not live to see it arrive. And we live inside this thing. Not above it, not beside it, not in some privileged position where we can see the whole structure laid out before us like a map. We live in the disk roughly halfway out from the center, embedded in one of the spiral arm regions, surrounded on all sides by stars, gas, dust, clouds, and a staggering amount of material that blocks, scatters, absorbs, and alters the light, trying to reach our eyes. Imagine trying to understand the layout of an entire city by standing in one apartment in the middle of one building with fog outside the windows and skyscrapers on every side. You might know your street very well. You might have a general sense of which direction the center lies. But the full map, the true shape of the thing you are inside, is inaccessible from your position. You need to step outside the city, entirely rise above it before the pattern becomes clear. We cannot do that. We are permanently inside. This matters enormously for what we can see. When we look at other galaxies, the Andromeda Galaxy, the Triangulum Galaxy, the Whirlpool Galaxy with its beautiful spiral arms, we are looking from outside. We see the whole structure. We can watch for changes across the entire disk. If a star explodes in Andromeda, it appears as a new bright point against a backdrop we know well. It stands out. The contrast is clean. But when we look at the Milky Way, when we look at our own galaxy's interior, we are peering sideways through thousands of light years of crowded, dusty disk. Stars overlap. Gas clouds interrupt our line of sight. Dust absorbs and scatters the very wavelengths our eyes are tuned to detect. And the busiest, most active regions, the ones most likely to host massive dying stars, are often the most heavily obscured. The center of our galaxy lies in the direction of the constellation Sagittarius, deep in the summer sky for those in the northern hemisphere. If you have ever stood under truly dark skies on a summer night and seen the Milky Way at its thickest and brightest, you are looking roughly in that direction toward the galactic center, toward the nucleus, toward the most densely packed, stellar territory our galaxy contains. And yet despite all that brightness, all that light scattered across the sky, you are seeing almost nothing of what is actually there. The galactic center itself is completely invisible to the naked eye and barely accessible even to optical telescopes. It is buried behind so much interstellar dust that visible light from the central region is extinguished by a factor of trillions before it can reach us. The center of our own galaxy is one of the most dramatic and active places in the Milky Way, and we cannot see it with our eyes. Not one photon of visible light from Sagittarius A times the 4 million solar mass black hole sitting at the heart of our galaxy has ever reached a human retina. That is the situation we are working within. That is the context inside which the question of missing supernovae must be understood. The Milky Way contains an estimated 200 to 400 billion stars, though the uncertainty in that number is itself staggering. The error bars span the entire population of a moderately large country. These stars are not distributed evenly. They cluster along the spiral arms, gather in the central bulge, thin out toward the outer edges. They form in dense molecular clouds, in regions rich with gas and the raw materials of stellar birth. And they tend to die where they were born because the stars most likely to die explosively, the massive ones, burn through their fuel so quickly that they never wander far from their birthplaces before collapsing. This means the places where supernovae are most likely to occur are often the same places that are most difficult for us to observe clearly. The spiral arms of the Milky Way are the most active star-forming regions. They are also full of gas and dust because stars form from gas and dust, and the supply is still abundant there. Massive stars born in these regions live their brief, spectacular lives surrounded by the same material that created them, then explode into it. The light from those explosions has to fight through all of that material before it can reach us. Sometimes it wins, often it does not. Now add the issue of distance. Our galaxy is enormous. A supernova on the far side of the Milky Way, 80,000 light-years away behind the galactic center, might be intrinsically as brilliant as any explosion in history, a stellar death that would have made our corner of the galaxy uninhabitable if it happened nearby. But by the time its visible light has crossed that distance, been absorbed, scattered, reddened, and dimmed by clouds of intervening material, it may arrive here as nothing obvious. Not a new star blazing in the sky, not even a reliable point of light. Perhaps a slight brightening somewhere in a crowded stellar field indistinguishable from ordinary variable stars without careful analysis. That is the geometry of our situation. We are not observers with a clear view. We are inhabitants of a complex, dusty, enormous system, looking out from one small corner of it, trying to catch events that may be happening on the other side of a structure 100,000 light-years wide. And yet this alone does not fully explain the 4 centuries of quiet, because not all supernovae happen at the far edge of the galaxy. Some happen in regions closer to us. Some happen in directions where the dust is thinner. Some should, by the broad statistics of stellar death, have occurred near enough and clearly enough to register not as a faint smudge in a professional telescope, but as a genuine new star, visible to anyone who happened to look up at the right moment. So the geometry explains part of the mystery, but only part. There are other layers beneath it. There is the question of how often these events actually happen, and how that rate is measured, and what it means in practice for any given stretch of human time. There is the question of what types of stars are candidates, and where in the galaxy they tend to live. There is the question of how many events may have occurred and been missed, not because they were hidden behind dust, but because our record-keeping was imperfect. Our skies were clouded, our attentions were elsewhere, or because we were simply looking in the wrong wavelength of light. And there is the deepest layer of all, the question of what we have become capable of seeing in the last few decades, not with our eyes, but with machines we have built to listen to the universe, in frequencies human biology never evolved to detect. Because the next supernova in the Milky Way, whenever it comes, may announce itself not as a bright new star in the night sky, but as a ghost of particles moving through granite, setting off detectors buried in Antarctic ice, or deep in Japanese mountains hours before the optical light reaches us. The question of the missing supernovae is not just a question about what has happened in the past. It is a question about what we are capable of witnessing now and what we might see next. All of that lies ahead. But before we can understand why we haven't seen one, we need to understand what exactly we are waiting for. What happens inside a star in the moments before it explodes? What forces are at work? What has been building sometimes for millions of years before the final second arrives? Because a supernova does not begin with a bang. It begins with a negotiation between gravity and light that every star is born into and that most stars will eventually lose. Every star you have ever seen with your naked eye is at its core a controlled catastrophe, a thing that should collapse under its own weight, held open by the sheer violence of nuclear fire. The balance is not peaceful. It is not stable in the way a rock sitting on a table is stable. It is stable the way a man is stable when he is running through constant enormous effort in defiance of the force that would bring him down the moment that effort stops. That force is gravity. And gravity never stops. To understand how a star dies, you have to understand how it lives. And to understand how it lives, you have to go back to the beginning, not the beginning of the universe, but the beginning of one particular star, in one particular region of space, at one particular moment, when the conditions align just right for something extraordinary to happen. Scattered throughout the Milky Way in the spaces between stars, there are vast clouds of gas and dust. These are called molecular clouds, because the material inside them is cold enough, often just a few degrees above absolute zero, that atoms have joined together into simple molecules, mostly hydrogen, some helium, traces of carbon, oxygen, nitrogen, and other elements forged in the interiors of earlier stars and scattered into space when those stars died. These clouds can span hundreds of light years. They contain more mass than millions of suns, and for the most part they sit quietly drifting through the galaxy in a state of cold, dark suspension. But they are not perfectly still. Turbulence moves through them, Shockwaves from distant stellar explosions ripple past and compress certain regions. The gravity of nearby objects tugs at their edges, and sometimes in some region of the cloud where the gas is slightly denser than the surrounding material, gravity begins to win a local argument. A pocket of gas starts to collapse inward. At first, this happens slowly. The material is spread over such an enormous volume that the motion is imperceptible on any human timescale. But as the gas compresses, its own gravity grows stronger. More material falls inward. The collapse accelerates. The center grows denser. Denser material pulls harder. The process feeds itself, building momentum over thousands and then millions of years, until what began as a diffuse smear of cold gas becomes something altogether different, a hot, dense, spinning ball of matter at the center of a flattening disk of leftover material. This is a protostar. Not yet a star. Not yet burning in the way a star burns, but already something remarkable. A world-sized object radiating heat from the energy of its own gravitational collapse, surrounded by a swirling disk of gas and dust from which planets may eventually form. The protostar is gathering mass, growing hotter, growing denser. Its core temperature is rising toward a threshold that will change everything. And when it reaches that threshold, when the temperature at the center climbs to approximately 10 million degrees Celsius, something ignites. Hydrogen begins to fuse into helium. This is the moment a star is born, not when it first forms from a cloud, not when it first starts to glow, but when nuclear fusion begins in its core, when the star discovers the process that will sustain it for millions or billions of years depending on its mass. The mechanism is worth pausing over because it is the key to everything that follows. In the core of a newly born star, hydrogen nuclei protons are moving at such tremendous speeds, and the density of matter is so extreme that they occasionally collide with enough force to overcome their natural electrical repulsion and fuse together. Through a sequence of reactions, 4 hydrogen nuclei are converted into one helium nucleus. The helium nucleus is slightly less massive than the 4 protons that created it. That missing mass does not disappear. It is converted into energy according to the relationship Einstein described. Energy equals mass times the speed of light squared. And the speed of light squared is an enormous number. The conversion of a tiny amount of mass releases an extraordinary amount of energy. That energy, generated continuously in the core, moves outward through the star as heat and radiation. It creates pressure, and that pressure pushes outward against the inward pull of gravity. This is the negotiation. This is the balance that defines a star's life. Gravity always pressing inward, always trying to compress the star to a point. Radiation pressure generated by the nuclear furnace in the core, always pushing back. As long as the core is producing enough energy, the star holds its shape. As long as there is hydrogen to burn, the negotiation continues. For our Sun, this negotiation has been ongoing for approximately 4.5 billion years. It will continue for roughly another 5 billion years before the hydrogen in the core becomes sufficiently depleted to shift the balance. In stellar terms, our Sun is a middle-aged star of modest temperament and reliable habits. It is by any fair assessment boring. This is entirely to our benefit. But the story changes dramatically when you consider stars born with much more mass. A star 10 times more massive than our Sun does not live 10 times as long. It lives roughly 1,000 times less long. The reason is counterintuitive until you understand the physics. A more massive star has stronger gravity. Stronger gravity compresses the core more tightly. A more tightly compressed core reaches higher temperatures. Higher temperatures mean faster nuclear reactions. Faster nuclear reactions mean the fuel is consumed at a staggering rate. The massive star has more hydrogen, yes, but it burns through it so recklessly, so extravagantly, that its total lifespan is a fraction of what a smaller star enjoys. A star 20 or 30 times the mass of the Sun might live for only a few million years. That sounds long by human standards. By stellar standards, it is barely an introduction. Our Sun has been burning for longer than the entire history of complex multicellular life on Earth, and it is nowhere near finished. A massive star, by comparison, lives fast, burns brilliantly, and dies young. While it lives, it is spectacular, These are the blue and white supergiants, the brilliant O-type and B-type stars that dominate the appearance of young star clusters. They are luminous beyond easy comparison. Some shine with the energy of millions of suns simultaneously. Their stellar winds are fierce-blowing material off their surfaces at thousands of kilometers per second. They illuminate and ionize the gas clouds around them, creating the glowing nebulae that appear in so many astronomy photographs. They are the rock stars of the stellar world, and like many rock stars, their brilliance is purchased at the cost of longevity. As a massive star burns through its core hydrogen, the balance begins to shift. The hydrogen supply diminishes. The energy output from the core decreases. Gravity presses inward and the core contracts slightly, but contraction raises the temperature, and a higher temperature opens a new door. Helium, the ash left behind by hydrogen burning, can itself be fused, but only at much higher temperatures. When the core contracts enough to reach those temperatures, helium fusion ignites. 3 helium nuclei fuse together to form carbon. Some carbon fuses with additional helium to form oxygen. The star has found a new fuel, and the negotiation continues. But helium burns faster than hydrogen. The core helium phase is shorter, and when the helium runs low, the core contracts again, temperatures rise again, and another threshold is crossed. Carbon begins to fuse, producing neon, magnesium, and other elements. Then neon fusion, then oxygen fusion producing silicon and sulfur, then silicon fusion. Each stage is shorter than the one before. Hydrogen burning in a massive star might last millions of years, helium burning perhaps 1 million years, carbon burning perhaps a few thousand years, oxygen burning measured in months, silicon burning measured in days. Inside this star by now the structure has grown deeply complex. Picture an onion, though a stranger one than any you have encountered in a kitchen. At the very center, silicon fusion is consuming its fuel in the final days of the star's nuclear life. Surrounding that a shell where oxygen still burns. Outside that shells of neon, carbon, helium and hydrogen burning in their own layers, each at its own temperature, each powered by its own fusion reactions, each producing ash that falls inward to become fuel for the shell below. The star has become, in a sense, a machine for working its way down the periodic table, from the lightest elements to heavier and heavier ones, each stage releasing less energy per reaction than the one before, each stage consuming its fuel more quickly, each stage pushing the star closer to a final crisis it cannot avoid. Because at the bottom of this sequence of fusion stages, waiting like a wall at the end of a corridor, is iron. Silicon fusion produces iron, and iron is where the story of stellar nuclear burning ends. Not because iron is rare or difficult to create. Iron is in fact among the most stable nuclei in existence. That stability is precisely the problem. All the previous fusion stages, hydrogen to helium, helium to carbon, carbon to neon, and so on, release energy because the products are more tightly bound than the ingredients. The fusion releases the difference in binding energy, and that energy is what holds the star open. But iron sits at the peak of nuclear binding energy. Fusing iron into heavier elements does not release energy, it consumes it. The moment the core of a massive star becomes dominated by iron, the nuclear furnace goes out. Not gradually, not with warning signs that give the star time to adapt. The fuel is simply gone. The energy source that has been fighting gravity for millions of years no longer exists, and gravity, which has been waiting with the patience of mathematics, moves in immediately. What happens next takes place in a time scale so compressed that it seems to belong to a different physical reality than the millions of years that preceded it. The iron core, no longer supported by nuclear pressure, begins to collapse. In less than a second, in fractions of a second, it falls inward. The outer regions of the core, still raining downward, follow. The density at the center surges past any material we can create or study on Earth, past the density of an atomic nucleus, into a regime where the normal rules of matter cease to apply. Electrons, which normally occupy the spaces between atomic nuclei, are forced together with protons under the crushing pressure. Quantum mechanics says that electrons cannot simply disappear, cannot all occupy the same energy state, but at these densities that resistance is overcome. Electrons and protons are merged into neutrons. In a process called neutronization, enormous numbers of neutrinos are produced and released. These neutrinos carry away vast quantities of energy, more energy than the sun will radiate across its entire lifetime in a pulse lasting only a few seconds. The inner core, now essentially a giant ball of neutrons, reaches a density at which it becomes incompressible. Neutron degeneracy pressure, a quantum mechanical phenomenon that prevents neutrons from occupying the same state, acts like a wall. The collapsing inner core bounces. The outer core, still falling inward, at a quarter of the speed of light slams into this wall and rebounds outward. A shockwave forms at the boundary. That shockwave begins moving outward through the star. It has the energy, in principle, to blow the entire outer envelope of the star into space. But the shockwave is also doing work. It is breaking apart heavy atomic nuclei as it moves through them, consuming energy. Without additional energy input, the shockwave may stall. This is one of the great outstanding problems in supernova physics. The shockwave should stall. By straightforward energy accounting, it does not always have enough power to complete its journey through the star's outer layers, and yet clearly many massive stars do explode. The remnants scattered across the galaxy testify to that. So something revives the shockwave. The leading candidate is the neutrinos. The pulse of neutrinos streaming outward from the collapsing core, containing more energy than can easily be imagined, passes through the stalling shockwave region. Most neutrinos interact with almost nothing. They pass through entire planets as though the planets were not there, but in the extreme density just behind the stalled shock, even the tiny fraction that do interact is enough. A small percentage of the neutrino energy is deposited into the material around the shockwave. That energy added to the shockwave may be what revives it, pushes it back to life, restores its momentum, and drives it outward through the remaining layers of the star. Simulations of this process are among the most computationally demanding calculations in astrophysics. The physics involve nuclear physics, quantum mechanics, general relativity, radiation transport, fluid dynamics. All operating simultaneously requires enormous supercomputers and still involves approximations. We do not yet have a complete, fully understood picture of exactly how the revival works in every case, but the broad outline is clear and supported by the observations of real supernova remnants we can study. The shockwave revived by neutrino energy continues outward. Hours pass. It travels through layer after layer of stellar material, through the oxygen shell, the carbon shell, the helium shell, the hydrogen envelope. As it moves, it compresses and heats the material it passes through, triggering explosive nucleosynthesis, more fusion reactions producing a zoo of new elements that are ejected into space along with the star's existing material. Finally, after hours of travel through the star's outer layers, the shockwave reaches the surface. The star's light output surges. The explosion becomes visible, and for days, then weeks, then months, the dying star, or rather, the expanding cloud of material that was the star, brightens, fades, evolves, changes color, and slowly disperses into the surrounding space. The numbers involved in this process sit outside ordinary intuition, and it is worth pausing to feel that properly. A massive star may contain more than 10 times the mass of our Sun. Our Sun alone has a mass of approximately 2 billion kilograms, a number so large that writing it in full would require 30 zeros. The star we are imagining has 10 or 20 or 30 times that. During the collapse, the inner core, roughly the mass of the Sun, compressed into a sphere, perhaps 20 kilometers across, collapses in less than a second. Consider what that means to Sun's mass, compressed to the size of a small city in under a second. If you tried to represent that process with a scale model, the star as a ball 1 meter across the collapse to neutron star proportional, the final collapsed object would be thinner than a human hair, and the time it takes would be at the same scale, a fraction of a millisecond. There is no everyday framework that accommodates this. Language borrowed from ordinary experience, fast, small, dense, hot, all fail here, not because they are wrong, but because the magnitudes involved are so far beyond their normal range of application that the words stretch thin and lose their grip. What you are left with is this: a star spends millions of years constructing the circumstances of its own death. It builds stage by stage the iron core that will eventually doom it. It exhausts each fuel source in turn, always running forward, never able to stop until it reaches the element that offers nothing more. And then, in a fraction of a second, the architecture of millions of years collapses, and in the minutes and hours that follow, the resulting explosion can outshine entire galaxies. There is something philosophically vertiginous about this, the patience of the build, the instantaneousness of the collapse, the vast quiet of millions of years ending in a second of violence that announces itself across intergalactic distances. When we ask why we haven't seen a supernova in the Milky Way recently, we are in part asking about this process, about where in all the stars scattered across our galaxy this sequence is currently playing out. Which stars have already built their iron cores, which are approaching that threshold, which have already crossed it, already exploded, and whose light is even now traveling toward us through the dark. But the collapse of a massive star's iron core is only one way a supernova can happen. There is a second path, quieter in its preparation, longer in its patience, and in many ways, stranger in its mechanics. A path that begins not with a star living extravagantly and dying young, but with a star that lived carefully, died quietly, and then after a long dormancy, returned for one final catastrophic statement. To understand the full picture of why our galaxy may be hiding its largest explosions, we need to understand both roads to stellar catastrophe. Because they happen in different places, involve different stars, and present different challenges for anyone trying to observe them from a small planet embedded in a dusty spiral arm looking out through thousands of light years of interstellar interference. The two families of supernova are not the same story. They are two different stories that share the same climax. There is a white dwarf sitting somewhere in the Milky Way right now, perhaps many thousands of them, that is quietly, incrementally doing something that will end in one of the most violent events the galaxy can produce. It is not obvious. It does not look dangerous. To any instrument scanning the sky in visible light, it appears as a faint point, cool and small and unremarkable, the kind of object that gets catalogued and forgotten, but it is gaining mass, slowly, patiently, gram by gram. It is crossing a distance toward a threshold that once reached cannot be uncrossed. When it gets there, it will not collapse first and explode second the way a massive star does. It will simply detonate, the entire star or nearly all of it, consumed in a thermonuclear runaway that tears it apart in seconds. This is the second road to supernova, and it begins not with birth but with death, or rather with what comes after a particular kind of death. When a star like our Sun reaches the end of its life, when the hydrogen in its core runs low and the balance tips, it does not explode. It is not massive enough for the iron core collapse we just described. Instead, it expands dramatically into a red giant, pulsing and shedding its outer layers into space in a slow, beautiful exhalation called a planetary nebula. The name is a historical accident. Early astronomers thought these glowing shells resembled planets through small telescopes, and the name stuck despite having nothing to do with planets. What remains at the center after the outer layers have drifted away is the exposed core of the former star. Dense, hot, no longer fusing anything in its interior. Roughly the size of Earth, but containing roughly the mass of the Sun. This is a white dwarf. The matter inside a white dwarf is compressed to a density that defies easy visualization. A single teaspoon of white dwarf material, if you could somehow scoop it up and bring it to Earth, which you cannot and should not attempt, would weigh approximately 5 tons. The electrons inside are packed so tightly that they enter a quantum mechanical state called electron degeneracy. In normal matter, you can compress atoms by forcing the electrons closer together. In degenerate matter, the electrons have been forced as close as quantum mechanics permits. They push back, not with heat or pressure in the ordinary thermodynamic sense, but with a fundamental quantum resistance to further compression. This is what holds a white dwarf up. Not fusion, not heat, pure quantum stubbornness. Left alone, a white dwarf simply cools. Over billions of years, it radiates its remaining heat into space. Eventually, in theory, it becomes a cold, dark sphere, a black dwarf, though the universe is not yet old enough for any to have fully cooled. White dwarfs are in this sense stellar embers. The fire has gone out. What remains is structure, memory, and heat slowly bleeding away into the dark. But many stars do not live alone. More than half of the stars in the Milky Way exist in binary systems. Two stars orbiting their common center of mass, sometimes close enough to interact directly, sometimes separated by distances large enough to accommodate entire solar systems between them. And when a binary system contains a white dwarf alongside a companion star that is still actively burning fuel, the situation can become over time deeply unstable. If the two stars are close enough, gas from the companion can flow toward the white dwarf. This happens through a process called mass transfer. The companion star, as it evolves and expands, begins to overflow the gravitational boundary that defines where its own gravity dominates versus the white dwarf's. Material spills across this boundary and falls onto the white dwarf's surface, accumulating in a thin shell. The white dwarf is gaining mass. Every year, every decade, every century, more material arrives. Now, recall what holds a white dwarf up. Electron degeneracy pressure, quantum mechanics resisting further compression. This resistance has a limit. As the white dwarf gains mass, its gravity increases. The electrons are pressed harder and harder against their quantum limit. The white dwarf counterintuitively shrinks as it gains mass, because in degenerate matter, more mass means stronger gravity, which means more compression, which means a smaller radius. And as the white dwarf approaches a critical mass approximately 1.4 times the mass of the Sun, a value known as the Chandrasekhar limit, after the physicist Subrahmanyan Chandrasekhar, who calculated it at the age of 19 while sailing from India to England in 1930, the situation approaches a point of no return. Near this limit, conditions in the white dwarf's interior become extreme enough for carbon fusion to ignite. But here is where white dwarfs differ catastrophically from ordinary stellar cores. In a normal star, if a region gets hotter, it expands, cools slightly, and the fusion rate moderates. The thermostat works. In a white dwarf, the pressure holding the star up is not temperature dependent. Degenerate matter does not respond to heating by expanding in the normal way. So, when carbon fusion ignites and releases heat, the temperature rises, the fusion rate increases. More heat is released, the temperature rises further, and there is no thermostat to moderate any of it. This is a thermonuclear runaway, a self-accelerating chain reaction that once started cannot be stopped. A flame of fusion sweeps through the white dwarf at a substantial fraction of the speed of sound inside the star. In seconds, not days, not hours, seconds, the entire star undergoes explosive nuclear burning. The energy released is enormous. The white dwarf is torn apart. It does not leave a neutron star behind as the core collapse of a massive star often does. In many cases, the white dwarf is completely obliterated. Nothing compact remains. Only an expanding cloud of newly synthesized elements, iron, nickel, silicon, and others racing outward into space. This is a Type Ia supernova, and it is, in certain respects, one of the most important tools in all of cosmology, because Type Ia supernovae are remarkably consistent in their peak brightness. The Chandrasekhar limit is a fixed number, a fundamental physical constant, the same everywhere in the universe. White dwarfs that explode at or near this limit release approximately the same amount of energy. They reach approximately the same peak luminosity. This makes them what astronomers call standard candles objects, whose true brightness is known, so that their apparent brightness, as seen from Earth, can be used to calculate their distance. The dimmer it looks, the farther away it is. Using Type Ia supernovae as standard candles, astronomers in the late 1990s, two competing teams led by Saul Perlmutter on one side and Brian Schmidt and Adam Rees on the other, measured the distances to supernovae in extremely distant galaxies. What they found overturned the existing picture of the universe. The expansion of the universe, rather than slowing down as expected under the influence of gravity, was accelerating. Something was pushing galaxies apart at an increasing rate. That something was given the name dark energy, a placeholder for something we still do not understand, and the discovery earned the 2011 Nobel Prize in Physics. So a dead star stealing mass from a companion, exploding in a thermonuclear catastrophe, and scattering iron across space also revealed one of the deepest mysteries in the history of science. The universe contains more strangeness than the stars alone. Now we have two roads. the core collapse of a massive star, the thermonuclear detonation of a white dwarf in a binary system. Both are called supernovae. Both can briefly outshine entire galaxies. Both scatter heavy elements into the interstellar medium and help seed future generations of stars and planets. But they are profoundly different events, arising from profoundly different progenitors occurring in profoundly different environments within the galaxy. And that difference in environment is exactly why understanding both types matters for our central question. Core collapse supernovae come from massive stars. Massive stars are short-lived. Because they die young, they die close to where they were born in the star-forming regions of the galaxy. The dense molecular clouds along the spiral arms, the regions rich in gas and dust. These are the very regions that are most obscured from our view. The same material that gives birth to massive stars, the gas and dust of stellar nurseries, is the material that blocks the light of their deaths from reaching us clearly. Think about what that means. The stars most likely to explode in a core collapse supernova are born in the dustiest, most optically opaque regions of the galaxy. They live their brief lives there millions of years rather than billions never wandering far. And they die there surrounded by the same clouds that created them, their light fighting uphill against layers of intervening material before it can reach our telescopes. Many of them never make it through cleanly. There is a compounding factor. Massive stars during their lives blow powerful stellar winds that sculpt the gas around them. They also, in some cases, shed enormous quantities of mass before they die, creating shells and clouds of circumstellar material surrounding the eventual explosion site. When the supernova does occur, its light must first penetrate this local cocoon of ejected material before it even reaches the broader interstellar medium. Some of this material absorbs and re-radiates the light at longer wavelengths infrared rather than visible, making the event harder to detect with ordinary optical telescopes, but potentially visible to infrared instruments. This is one reason why infrared astronomy has become so important to the search for hidden supernovae in the Milky Way. The light that visible wavelengths cannot carry through infrared wavelengths sometimes can. Type Ia supernovae present a different observational challenge. White dwarfs come from smaller stars, stars like our Sun or somewhat more massive, which end their lives without a dramatic explosion and leave behind these dense remnants. Smaller stars live longer, billions of years in many cases. That means white dwarfs can exist in stellar populations that formed long ago in regions that have since dispersed, cleared of gas and dust, and aged into quieter territory. Type Ia supernovae can therefore occur in older stellar populations, the galactic bulge, the halo, the thick disk, in regions that may be less obscured by active star formation. But type Ia supernovae bring their own complications. The binary systems that produce them are before the explosion thoroughly unspectacular. A white dwarf gaining mass from a companion does not announce itself. There is no bloated red supergiant to point to, no unstable surface activity, no clear signpost saying this system will detonate. The explosion, when it comes, is sudden, emerging from an ordinary-looking binary system with little warning detectable by current instruments. We cannot easily compile a list of type Ia candidates the way we can gesture at a red supergiant and say that one eventually. There is also genuine scientific debate about the precise progenitor channels for type Ia supernovae. The single degenerate scenario, one white dwarf gaining mass from a companion star, is one possibility. But another channel, the double degenerate scenario, involves two white dwarfs in a binary system spiraling toward each other as they lose energy through gravitational wave emission. Eventually they merge, and if the combined mass exceeds the critical limit, a thermonuclear explosion follows. Identifying which channel dominates and in what proportion is an active area of research with significant implications for how we model supernova rates in different types of galaxies. What both types share, and what matters most for understanding the silence in our sky, is that their observability from our position inside the Milky Way depends enormously on where in the galaxy they occur and what lies between us. Explosion site. A core collapse supernova happening in a spiral arm on the far side of the galactic center might be intrinsically as luminous as the famous events ancient astronomers recorded, but it occurs behind tens of thousands of light-years of dusty galactic disk, behind the dense stellar and gas concentrations of the galactic center itself. The extinction, the dimming of its visible light by intervening material could be a factor of billions or more. An event that would have dominated the night sky from nearby becomes from Earth something that does not even register on optical instruments. A Type Ia supernova occurring in the galactic bulge faces similar challenges. The bulge is densely populated with old stars, an ideal environment for white dwarf binary systems, but it is also located in one of the most optically obscured regions of the sky behind the same dust lanes that make the galactic center invisible to human eyes. And here is the uncomfortable arithmetic. The regions of the galaxy most likely to host supernovae of either type, the star-forming spiral arms for core collapse events, the dense old stellar populations of the bulge for Type Ia events, are by no coincidence the regions most difficult for us to observe clearly in visible light. The galaxy has arranged its most dramatic events behind its thickest curtains. This is not a conspiracy. It is geometry combined with the physical fact that stars form from gas and dust are what block our view. But the effect is real, and it profoundly shapes what we have seen and what we have missed. Now add the question of rates. Astronomers estimate that the Milky Way should produce on the order of 2 core collapse supernovae per century, with significant uncertainty. In that number, observations of radioactive aluminum, 2-6, throughout the galactic disk made by the European Space Agency's integral satellite support a rate in that approximate range. Type Ia supernovae add to the total, though their rate is somewhat lower and harder to constrain directly. Combined, the expectation is that our galaxy should be producing several supernovae per century. Several per century sounds reassuring. It sounds like we should have seen something by now. But several per century is not the same as several visible from Earth per century. Once dust extinction is accounted for, once the fraction of events occurring in the most obscured regions is considered, once the probability of events occurring at distances so great that even unobscured they would be modest in apparent brightness is factored in, the fraction that would produce a dramatic naked eye display shrinks considerably, perhaps to 1 or 2 per century that would have been obviously visible under good conditions, perhaps to fewer. And then consider the randomness, the genuine irreducible randomness of when events occur within a rate distribution. Even if the true rate were exactly 2 dramatic visible supernovae per century, you might go 3 centuries without one. You might go 4. Not because the rate has changed, not because the galaxy has gone quiet, simply because randomness produces gaps, and gaps can stretch. The gap since 1604 4 centuries is long, but it is not, given all of these factors, impossible. It is in fact arguably expected once you account for the difference between how often supernovae occur in the Milky Way and how often we should expect to clearly see one from where we are sitting. The silence begins to make sense. Not complete sense, the gap is still at the longer end of what models would predict for naked eye events, but not shocking sense. Not something is fundamentally wrong sense. More likely, what the 4 centuries of quiet reflects is a combination of all these factors operating together. The geometry of our position inside a dusty disk, the preference of the most likely supernova sites for the most obscured regions, the random spacing of events within a rate distribution, and the possibility, which we will examine closely, that some events did occur during this period and were simply hidden from ordinary sight. Because there is one final point that reshapes the entire question. The 2 types of supernovae we have been discussing are not equally invisible when they are obscured. A core collapse supernova, whatever visible light the dust may steal, produces an extraordinary burst of neutrinos. Those neutrinos, as we noted earlier, pass through essentially everything. Thousands of light years of interstellar dust is nothing to a neutrino. Rock, water, lead, all irrelevant. If a core collapse supernova occurred in the Milky Way tonight behind every dust cloud in the galaxy on the opposite side of the galactic center from us, the neutrinos would arrive here in essentially full force, detectably within hours. We have detectors that can catch them. That means the next core collapse supernova in the Milky Way, whenever it comes, may not be hidden from science, even if it is hidden from human eyes. The neutrinos will arrive. The detectors will register. The alerts will go out. And while the rest of humanity wonders why astronomers are suddenly very excited about something that looks faint and reddish near Sagittarius, the scientists will already know what happened. The two roads to supernova, then, are not just different mechanisms, they are different stories about what we can and cannot see, what we can and cannot predict, and how our instruments have changed the terms of waiting. A white dwarf exploding in a clean nearby region of the galaxy would give us a spectacular naked eye event. A massive star collapsing behind the galactic center would give us something invisible to casual observers, but deeply informative to science. Either way, the galaxy keeps its schedule, regardless of our instruments or our impatience. The question is simply whether, when the next event comes, we will understand what we are seeing and whether we will have built the right tools to catch what our eyes cannot. The dust that hides so many of these events is not a passive backdrop. It is one of the most important physical features of the galaxy. And to understand why 4 centuries of silence is less mysterious than it first appears, we need to look at that dust directly to understand what it is, where it lives, and exactly how thoroughly it can erase even the most violent stellar event from human sight. Hold a single grain of sand between your fingers. Feel how small it is, how easily it disappears against the skin, how the light barely bothers to acknowledge it. Now, imagine something smaller still, 1,000 times smaller. A particle so tiny that a human hair laid beside it would look like a highway next to a bicycle lane. A grain so small that it drifts through space not under the dominance of gravity but carried by radiation pressure, nudged by stellar winds, suspended in the vast cold between stars, like dust motes hanging in a sunlit room, except the room is thousands of light years across, and the sunlight comes from 100 billion directions at once. That is interstellar dust, not metaphorical dust, not the shorthand astronomers sometimes use when they mean something complicated. Actual solid particles, tiny grains of carbon compounds, silicates, polycyclic aromatic hydrocarbons, water, ice coatings, and other materials floating through the space between stars, in concentrations that are, by any earthly standard, almost incomprehensibly thin. In the densest interstellar dust clouds, there are perhaps 1,000 grains per cubic kilometer. A cubic kilometer of the thickest interstellar medium contains less solid matter than a single snowflake, and yet this almost nothing stretched across thousands of light years becomes a wall. The physics is straightforward. When a photon of visible light, a particle of the light your eyes use to see, encounters an interstellar dust grain, several things can happen. It can be absorbed, its energy converted to heat in the grain. It can be scattered, deflected from its original path at a new angle, or it can pass by unaffected, continuing on its journey. Which outcome occurs depends on the relationship between the photon's wavelength and the size of the grain. Grains that are roughly the same size as the wavelength of the incoming light interact with it most strongly. And interstellar dust grains, typically between 1/10 and 1,000th the wavelength of visible light, are extraordinarily effective at interacting with exactly the wavelengths the human eye is designed to detect. Blue light, with its shorter wavelength, is scattered and absorbed more efficiently than red light. Red light, with its longer wavelength, passes through more easily than blue. This means that when starlight travels through a dusty region of space, the blue end of the spectrum is preferentially removed, and what arrives at the other end is reddened, shifted toward the red end of the spectrum, dimmer than it started. Its colors altered, its intensity reduced. Astronomers call this interstellar reddening and extinction. It is one of the most pervasive effects in observational astronomy and one of the most important reasons why the Milky Way looks nothing like what it actually is. The extinction is not linear with distance. It compounds. Every additional light year of dusty material adds more extinction. Toward the galactic center, through the maximum depth of the galactic disk, through the most active star-forming regions, through the densest concentrations of interstellar material, the visual extinction reaches values that are not merely inconvenient for observation, but fundamentally prohibitive. The visible light from stars at the galactic center is extinguished by a factor of approximately 1 trillion compared to what it would be without dust. 1 trillion. An object that would otherwise appear as one of the brightest stars in the sky becomes completely invisible to human eyes and to any telescope operating in visible wavelengths. The center of our own galaxy, the heart of the system we live in, 4 million solar masses of black holes surrounded by dense clusters of young stars and complex molecular chemistry, cannot be seen, not with the naked eye, not with the best optical telescope ever built. The light simply does not survive the journey. This is the environment through which supernova light must travel, and the problem is not limited to the galactic center. It applies in varying degrees to much of the galactic disk. Our Sun sits roughly 26000 light-years from the galactic center, embedded in the disk at a location that places us neither particularly close to the center nor particularly far out toward the edges. When we look in any direction along the plane of the galaxy, when we look toward the rich, bright band of the Milky Way that stretches across the night sky, we are looking through the disk, through layer upon layer of gas and dust, through star-forming regions and molecular clouds, and the accumulated debris of billions of years of stellar activity. The extinction varies dramatically depending on exactly where we look. Some directions along the galactic plane are relatively clear windows, where the dust is thinner, where we can see deeper into the disk. Astronomers have catalogued these windows and given them names. Bard's window toward the galactic bulge is one of the most famous, a region where extinction is low enough to permit study of the stellar populations near the galactic center, a gap in an otherwise formidable curtain. But even Bard's window reduces the light from objects behind it by a factor of roughly 10 compared to an unobscured line of sight. And it is exceptional. Most directions toward the inner galaxy are far more opaque. Now place a supernova somewhere in this environment. Place it, say, on the far side of the galactic center, 80,000 light-years away, in one of the inner spiral arms, in a region where star formation is active and massive stars are plentiful. The explosion occurs. For anyone close enough to observe it, unobscured, it would be extraordinary. A point of light appearing in the sky, brighter than a full moon visible in daylight, casting shadows at night, persisting for months. A stellar death, announced across the neighborhood of space, with the authority that only a dying massive star can project. Now follow the visible light from that explosion as it travels toward us. It moves at the speed of light. There is no other speed available to it crossing the 80,000 light-years between the explosion and Earth, a journey that will take 80,000 years. Along the way, it passes through the galactic center region, through thick concentrations of molecular clouds, through dust lanes that cut across spiral arms, through the accumulated interstellar material of a disk that has been building complexity for billions of years. By the time it arrives here, virtually nothing remains of the visible light that set out from the explosion site. The extinction has been so severe, so comprehensive, so relentless across so many light-years of absorbing material that what was once bright enough to rival the moon has been reduced to something below the threshold of even the most sensitive optical telescope. The explosion happened. The light arrived, but no human eye and no optical instrument would ever know. The neutrinos from that same explosion, if it was a core collapse event, would arrive here intact, unimpeded, detectable by the right instruments. But the light is gone. This is not a hypothetical edge case. This is the expected experience of a significant fraction of all supernovae occurring in the Milky Way. The inner galaxy, where the supernova rate is highest, because that is where the most stars are, where the spiral arms are densest, where the star formation is most active, is also the region most thoroughly obscured from our view. The galaxy has, through no malice, but through straightforward physics, arranged things so that the most likely explosion sites are the least visible ones. Infrared light changes this picture partially. Infrared photons have longer wavelengths than visible light, longer than red, longer than what the human eye can detect, and they interact less efficiently with dust grains. They are not immune to extinction, but they are far more resistant to it. A region that is completely opaque to visible light may be observable in the near-infrared. A region opaque to near-infrared may transmit mid-infrared. As you move to longer and longer wavelengths, you penetrate progressively deeper into dusty regions that were previously invisible. This is why some of the most important observations of the galactic center have come not from optical telescopes, but from infrared instruments, the Sofia Airborne Observatory, the Spitzer Space Telescope, ground-based instruments, equipped with infrared detectors. In infrared light, the galactic center transforms. Dust lanes that block all visible light become transparent. Dense stellar clusters emerge that were previously hidden. The architecture of our galaxy's core becomes visible in a way that ordinary observation never permitted. Radio waves go further still. Radio wavelengths are so much longer than dust grain sizes that interstellar dust has almost no effect on them. Radio telescopes can peer through the galactic center as though the dust were not there, and much of what we know about the structure of the inner Milky Way, about the molecular clouds and star-forming regions and expanding shells of old supernova remnants near the galactic core, comes from radio, observations that visible light could never have provided. X-ray and gamma-ray observations add yet another layer. High-energy photons can sometimes penetrate material that blocks lower-energy light. Neutrinos, as we have discussed, penetrate essentially everything. Modern astronomy is a multi-wavelength enterprise, not merely because astronomers enjoy collecting instruments, though they do, but because no single window onto the electromagnetic spectrum shows the complete picture. Each wavelength reveals structures and events invisible to the others. The galaxy is not one thing that different instruments see differently. It is many things layered on top of each other, each layer visible only to the right kind of eye. And what the right kinds of eyes have revealed in the decades since astronomers began systematically surveying the sky at non-visible wavelengths is deeply relevant to our question. In 1985, radio astronomers discovered a small bright source in the inner galaxy designated G1-9 plus 0.3, a name that encodes its position in galactic coordinates, the kind of designation that only a person who has never tried to explain astronomy to a child could find satisfying. At first, it attracted modest interest. There are many radio sources in the inner galaxy. Many are the remnants of old supernovae, expanding shells of shocked gas that glow at radio wavelengths long after the visible event has faded. But G1-9 plus 0.3 was unusual. When astronomers compared radio observations made in 1985 with observations made in 2007 and 2008 using the Very Large Array in New Mexico and the Chandra X-ray Observatory, they found that the remnant had grown, not by a small amount, by approximately 16% in apparent size over roughly 2 decades. For a supernova remnant, this is extraordinarily fast. The expansion rate implied an explosion velocity of several percent of the speed of light, and the degree of expansion worked backward through time pointed to an explosion that had occurred approximately 100 to 150 years before the 2008 observations, sometime in the late 19th or very early 20th century. Sit with that for a moment. Somewhere in the inner Milky Way, roughly in the direction of the galactic center, a star exploded sometime around 1870 to 1900. An event that, if it had occurred in a clear region of the sky, might have been one of the most dramatic astronomical events in modern history. Visible, perhaps in daylight, certainly as a brilliant new star at night, covered in newspapers, observed by every professional astronomer alive. An event that would have been, by the standards of the time, extraordinary, and almost no one noticed. The reason is as simple as it is instructive. G1-9 plus 0.3 lies in the direction of the galactic center at a distance of approximately 28000 light-years deep behind the dust curtain that makes the inner galaxy invisible to optical astronomy. The visible light from the explosion was extinguished before it could travel even a fraction of the distance to Earth. Whatever bright display occurred at the explosion site, and for a supernova, it would have been immense. The light simply never arrived here in a form that human eyes or the optical instruments of the late 19th century could detect. A star died. The galaxy registered it. We did not. G1-9 plus 0.3 is currently the youngest known supernova remnant in the Milky Way. The explosion it marks occurred within what many of us would consider living memory within the lifetimes of great-grandparents. and yet it entered the scientific literature, not as a dramatic contemporary event witnessed in real time, but as a forensic discovery made a century after the fact, reconstructed from the expanding shell of shocked gas it left behind. This is what hidden means in the context of galactic supernovae, not hidden in the sense of invisible to all instruments, hidden in the sense of invisible to the instruments and senses humans were actually using at the time of the event. The galaxy did not conspire to conceal it. The physics of interstellar dust simply ensured that the most obvious messenger visible light never made it through. The remnant waited, expanding quietly through the inner galaxy until radio and X-ray telescopes of sufficient sensitivity came along to find it. How many other such events have occurred? How many supernovae have taken place in the Milky Way over the past 4 centuries behind dust lanes that stripped away the visible light before it could reach us, their remnants now expanding quietly through the inner galaxy, waiting for sufficiently powerful instruments to find them? We do not know the precise number. The galactic plane is large, and surveying it comprehensively for faint, confused, overlapping radio and X-ray sources in the direction of the galactic center is technically demanding, but the known supernova remnant population of the Milky Way, currently numbering in the hundreds, with new candidates identified regularly, already tells us something important. Many of these remnants have no associated historical observation, no record of a new star in the sky, no account of unusual celestial activity at the time the explosion would have been visible from Earth. They are orphaned events, physical facts without human witnesses, stellar deaths that occurred beyond the reach of whatever observational tools existed at the time. Some of these orphaned remnants are genuinely ancient explosions that occurred before writing, before cities, before the human tendency to look up and record what we saw had found a reliable medium for preservation, but others are less ancient. Some remnants have ages of a few hundred years. Some could, in principle, have produced brief, visible displays that went unrecorded, or were recorded in documents that did not survive, or occurred in directions where they were simply not noticed amid the complexity of the sky. The silence since 1604 may not be a silence at all. It may be a conversation happening in frequencies we were not until recently equipped to hear. There is a lesson in this that extends beyond astronomy, though astronomy teaches it with particular clarity. We tend to assume that the absence of evidence is evidence of absence. If no one recorded a supernova between 1604 and the present, then no supernova occurred that was worth recording. But this reasoning assumes that our recording systems were complete, that anything significant enough to record would have been recorded, that our instruments were sensitive enough, our coverage comprehensive enough, our archives complete enough to capture everything that happened. None of these assumptions hold. Visible light is one narrow band in the electromagnetic spectrum. It is the band our eyes evolved to detect because it is the band in which the sun emits most of its energy, a practical adaptation, not a cosmic privilege. The universe communicates in radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, neutrinos, and gravitational waves. For most of human history, we could hear only one of these channels. We listened carefully and attentively to that one channel, and we heard what it had to offer. But the channels we could not hear were transmitting continuously, carrying information about events we never knew were happening. Every time astronomy has opened a new wavelength window, radio in the mid-20th century, X-ray and infrared from space in the late 20th century, neutrino detection, gravitational wave detection in the 21st, the universe has revealed phenomena that the previous instruments could not see. Not because those phenomena were rare or exotic, but because they were there all along, broadcasting in frequencies no one had yet learned to receive. The inner Milky Way, hidden behind its dust curtain, is one of the most dramatic examples of this principle. It is not a quiet place. Radio observations show it to be intensely active, turbulent, magnetized, punctuated by expanding shells and filaments, and the relics of old explosions. X-ray observations reveal hot plasma energetic processes, the signatures of violent events. Infrared surveys map dense stellar clusters and complex molecular chemistry. The galactic center is one of the most dynamic and extreme environments in the entire galaxy. We simply could not see any of it until we learned to look in the right ways. The supernova that created G1 9 plus 0.3, was not a marginal event. It was a genuine stellar explosion, the death of a massive star, an event that released more energy in seconds than the sun will emit across billions of years. It occurred within the modern era, within the period when human civilization had scientific institutions, professional observatories, systematic sky surveys, and the cultural habit of recording and publishing unusual celestial observations. And it went undetected until decades after the fact. If that can happen once, it can happen again. And it may have happened before G129 plus 0.3. Other explosions in the inner galaxy, other remnants not yet identified, other stellar deaths that occurred without leaving any trace in the human record because the light taken before it could arrive. The 4 centuries since Kepler's supernova are not then a mystery that demands an exotic explanation. They do not require the galaxy to have gone quiet or stellar evolution to have paused, or some unknown physics to have changed the rate of massive star death. They require only the mundane facts of dust distance geometry and the limitations of instruments built by creatures whose eyes evolved to see in the narrow band of light that happens to be most effectively blocked by interstellar grain. The galaxy has been working the entire time. We have been listening through a keyhole. But there is another layer to the mystery, still one that does not involve hidden events or obscured light. One that involves the events we did witness, the ones that made it through the dust and the distance and the randomness, and arrived in human eyes with their full drama intact. Because before the silence fell, humans saw these things. They stood outside under skies, unmediated by electric light, looked up and watched stars die. They wrote down what they saw. They argued about what it meant. And some of what they recorded has become foundational to our understanding of the universe. Sometime in the spring of the year 1006, a scholar living in the city of Al-Qahira, the city we now call Cairo, stepped outside before dawn and saw something in the southern sky that had not been there the night before. He was not alone in noticing it. Across the width of the known world, from the observatories of Islamic astronomers in Egypt and Iraq to the monasteries of medieval Europe, from the imperial courts of China to the temples of Japan, from the scriptoria of Swiss monks to the cliff dwellings of people living in what is now the American Southwest, people looked up and saw the same thing, a new star. A star so bright, it defied the categories available to describe it. The Egyptian astronomer Ali ibn Ridwan, writing carefully about what he observed, described a spectacle roughly 2.5 to 3 times the apparent size of Venus, with light that he said was like the light of the moon in its first quarter, bright enough to cast shadows at night, bright enough in the accounts of some observers to read by. It appeared in the constellation we now call Lupus, not far from the plane of the Milky Way, and it remained visible, gradually fading for months. Some accounts suggest it was visible for as long as 2 years before it finally disappeared entirely from unaided sight. What those observers were watching was a stellar explosion approximately 7100 light-years away. The light they saw had left its source during the era of the Roman Empire, traveling across 7,000 years of dark space before arriving at Earth in the year 1006 and announcing itself to every civilization simultaneously, capable of looking up and writing down what they saw. The star that produced it, a white dwarf that had accumulated enough mass to trigger catastrophic thermonuclear burning, was gone, torn apart, scattered into space as an expanding cloud of iron and silicon and the other products of its final nuclear fire. We know now that this event, designated SN 1006, was almost certainly the brightest supernova in recorded human history. By modern estimates, it reached an apparent visual magnitude of somewhere between -7 and -8, far brighter than Venus, which typically reaches about -4 at its brightest. By comparison, the full moon sits at approximately -13. SN 1006 was not as bright as the moon, but it was the brightest point source of light in the night sky, by an enormous margin. It would have been visible in daylight. It would have been visible on nights when thin clouds obscured most stars. It would have been, for anyone paying attention, completely unmistakable. The remnant of that explosion still exists. Designated SNR 1006, It now appears as a roughly circular shell of X-ray and radio emission, expanding through the interstellar medium at thousands of kilometers per second, more than 1,000 years after the explosion that created it. When modern X-ray observatories turn their instruments toward it, they see the shock front where the expanding debris is slamming into surrounding gas, heating it to temperatures of millions of degrees. They see the blue glow of synchrotron radiation electrons accelerated to near light speed by the explosion's magnetic fields. They see the ongoing consequence of a moment that human beings watched from their rooftops and their fields and their observatories more than 1,000 years ago. The continuity is extraordinary. A person in medieval Cairo looked up and saw a new light. A satellite in Earth orbit 1,000 years later maps the expanding shell that light came from. One event. An unbroken thread of human curiosity connecting the two ends of a millennium. 48 years later, in July of 1054, Chinese imperial astronomers recorded the appearance of another guest star, their term for transient celestial visitors, which is both poetically apt and scientifically precise in a way that takes a moment to appreciate. This one appeared in the constellation we now call Taurus, not far from the tip of the bull's upper horn. The Song dynasty records describe it as visible in daylight for 23 days and at night for approximately 2 years before fading from view. Japanese and Arabic sources corroborate the observation. The astronomer Yang Weidi, who reported the sighting to the imperial court, described a star with rays of light emanating from it in 5 colors, alternating between yellowing and white. The remnant of the 1054 explosion is one of the most studied objects in the entire sky. We call it the Crab Nebula. When you look at photographs of the Crab Nebula, the intricate tangled web of glowing gas filaments, the bright inner torus, the blue-white glow of synchrotron radiation permeating the entire structure, you are looking at the debris of a star, not figuratively. Literally, the material that was once inside a massive star, scattered into space by the shockwave of its death, now expanding outward at approximately 1500 kilometers per second. The Crab Nebula is currently about 11 light-years across. When the explosion occurred, all of that material was concentrated in a volume smaller than the Sun. In the roughly 970 years since it has expanded into a structure vast enough that light itself takes 11 years to cross it. At the center of the Crab Nebula sits the Crab Pulsar, the collapsed remnant of the star that exploded a neutron star, roughly 20 kilometers across, spinning approximately 30 times per second. As it spins, it emits beams of radiation from its magnetic poles. If those beams sweep past Earth with each rotation, which they do, we detect them as regular pulses of radio waves, visible light X-rays, and gamma rays, arriving 30 times per second with a regularity that makes atomic clocks look imprecise. The Crab Pulsar is one of the most precisely timed objects in the universe. It has been spinning and pulsing continuously since the day the explosion occurred. It was spinning when the light reached Earth in 1054. It was spinning when medieval Chinese astronomers recorded their guest star. It is spinning right now at this moment as you read this. The fact that we can study the neutron star left behind by a supernova that human beings watched in 1054 is one of the most remarkable continuities in all of science. The dead star is still there. It did not vanish with the light. It persisted spinning, pulsing, pouring energy into the nebula around it, waiting for us to develop the instruments to find it. 5 centuries passed between the Crab supernova and the next major stellar explosion to enter the historical record with force. In those 5 centuries, astronomy remained largely the same. Discipline, careful, naked-eye observation, patient recording of celestial positions, the slow accumulation of data about planetary motions and stellar positions. The sky was watched, but no new star of extraordinary brightness appeared to demand attention. Then, in November of 1572, a young Danish nobleman named Tycho Brahe stepped outside after dinner and saw something that stopped him. He was 25 years old. He had already demonstrated an unusual aptitude for careful observation and an unusual impatience with imprecision qualities that would define his career. He knew the night sky with the intimacy of a man who had spent years memorizing it. and there in the constellation Cassiopeia, in a position where no star of comparable brightness had any right to be, was a new light. His first instinct was disbelief. He asked the servants walking with him whether they could see it too. They could. He stopped passing peasants and asked the same question. They confirmed what he was seeing. Only then did he accept that the sky had genuinely changed, and he began what would become one of the most important observational programs in the history of astronomy. Tycho's contribution was not merely that he noticed the new star. Many people noticed it. The object was bright enough to be visible in daylight for weeks, and it remained visible to the naked eye for approximately 16 months before fading entirely. His contribution was that he measured it, night after night, with the finest instruments available in the pre-telescope era. He carefully determined the position of the new star relative to the fixed stars of Cassiopeia. He was looking for parallax, a shift in apparent position as the Earth moved through its orbit that would betray the object's proximity. If the new star were nearby within the Earth's atmosphere, or close to the Moon, parallax would reveal it. The object would appear to shift slightly against the background of more distant stars as the observer's position changed. Tycho found no parallax, none detectable by his instruments. The new star sat fixed among the distant stars of Cassiopeia, moving only as the constellation moved, which is to say not at all relative to the other stars. It was not a comet. It was not an atmospheric phenomenon. It was genuinely located among the stars. The heavens, which Aristotelian philosophy held to be changeless and perfect above the lunar sphere, had changed. The significance of this conclusion was not lost on Tycho or on his contemporaries. The idea that the celestial realm was incorruptible, that change and decay belonged only to the sublunar world of Earth, was one of the foundational assumptions of European natural philosophy. A new star appearing among the fixed stars and then fading away was not merely an astronomical observation, it was a philosophical crisis. The sky was not what it had been assumed to be. The heavens were subject to change. The architecture of the cosmos inherited from ancient authority had a crack in it. Tycho published his observations in a book titled De Nova Stella on the New Star in 1573. The term he used, nova stella, gave us the word nova and eventually supernova. He was, without knowing it, naming a category of phenomena that would not be physically understood for another 4 centuries. The remnant of Tycho's supernova, officially designated SN 1572, but often called Tycho's supernova remnant, is still observable today in radio, optical, and X-ray wavelengths. It lies approximately 8,000 light-years away in Cassiopeia. X-ray observations by the Chandra telescope reveal the expanding blast wave and the reverse shock propagating back into the ejected material. The detailed chemistry of the remnant, particularly the pattern of iron and other elements in the ejector, strongly supports its identification as a type Ia supernova, the thermonuclear destruction of a white dwarf that had accumulated too much mass from a binary companion. A dead star that returned for one last statement, and in doing so helped dismantle a worldview. 32 years after Tycho's supernova faded from view, the sky offered one more, the last one, as it turned out, for at least 400 years. In October of 1604, a new star appeared in the constellation Ophiuchus, the Serpent Bearer, a large and often overlooked constellation straddling the celestial equator. It appeared near a conjunction of Jupiter, Saturn, and Mars, which had already attracted the attention of astrologers and astronomers across Europe. Johannes Kepler, then 33 years old and working in Prague as imperial mathematician to the Holy Roman Emperor Rudolf II, first saw it on October 17th. Though other observers had noticed it days earlier, he immediately recognized its significance and began systematic observations that would continue for over a year. Kepler was not the first to observe it. Italian astronomer Ilario Altobelli saw it on October 9th. Galileo Galilei, then 40 years old and teaching mathematics in Padua, also observed it and gave public lectures about its implications. Across Europe, in the Ottoman Empire, in China, in Korea, the new star was noticed, recorded, discussed, and argued over. Its peak brightness rivaled Jupiter, making it one of the brightest objects in the night sky, like Tycho's star before it. It was visible in daylight for a brief period, but it was Kepler's observations that became most famous, partly because of his meticulous record-keeping and partly because of what he wrote about the event. Kepler, like Tycho before him, measured the star carefully for parallax and found none. It was a true stellar object, not an atmospheric phenomenon, and Kepler was living through a moment when the old cosmology was already fracturing under the pressure of new evidence. Copernicus had argued that the Earth moved around the Sun. Tycho had shown the heavens could change. Now, another new star had appeared. Kepler published his observations in a work called De Stella Nova, echoing Tycho's title consciously and deliberately. He measured, he calculated, he speculated about the star's nature, with the tools available to him, which did not include any concept of nuclear physics, neutron stars, stellar evolution, or the electromagnetic spectrum, beyond visible, to light. He interpreted what he saw through the frameworks of his time, mixing careful empirical observation with astrological speculation and theological reflection in a combination that seems jarring by modern standards, but was entirely natural to a 17th century thinker trying to make sense of an anomaly. What he could not have known was that the light reaching his eyes had left its source approximately 130000 years earlier, during the last ice age, when the ancestors of the people who would build his city were painting animals on cave walls. That star had died before agriculture, before writing, before any human institution he would have recognized as civilization. It had been traveling across space in the dark ever since unwitnessed, unreceived, carrying its ancient news through the void until the autumn of 1604, when it finally arrived at a planet that had just recently developed the habit of writing things down carefully. Kepler's supernova, the event we now formally designate SN 1604, was most likely another type Ia supernova. Like Tycho's star before it, spectroscopic analysis of its remnant reveals the chemical fingerprint of a thermonuclear explosion rather than a core collapse. The iron-rich ejecta, the absence of a compact neutron star at the center, the structure of the expanding shell, all point to a white dwarf that crossed its fatal threshold and detonated. The remnant is observable today at a distance of approximately 2,000,000 light-years, detectable in radio-optical infrared and X-ray wavelengths, its expanding shockwave still moving through the surrounding interstellar medium, more than 4 centuries after the light first reached Kepler's eyes. Since that October night in 1604, the Milky Way has offered no comparable spectacle. No new star has blazed into prominence. No new light has appeared in the night sky bright enough to demand notice from anyone with eyes and a clear view. In the 4 centuries that followed, humanity developed the telescope, spectroscopy, photography, radio, astronomy, space telescopes, digital detectors, automated sky surveys, particle physics, quantum mechanics, general relativity, and the ability to detect neutrinos passing through the Earth's crust. We became, by any reasonable measure, the most observationally capable civilization in human history. And our own galaxy has not given us a naked eye supernova since before all of it. The contrast is worth holding. In the 6 centuries between 1006 and 1604, humans witnessed at least 4 clear galactic supernovae: SN 1006, SN 1054, SN 1000, 572 and SN 1604, possibly more depending on how one interprets less certain historical records. In the 4 centuries, since none that are unambiguous. The visible silence has outlasted every scientific revolution, every technological transformation, every generational turnover in the human story. But the historical record teaches something else as well, something that complicates easy conclusions. Notice which civilizations observed these events most thoroughly and most reliably. The records from Chinese imperial astronomy are often the most detailed and systematic. Islamic scholars produced careful observations of SN 1006 and SN 1054. European records are patchier, sometimes rich, sometimes strikingly sparse for events that must have been visible across the continent. Native American oral traditions and rock art suggest observations of at least the 1054 event by peoples in the American Southwest. The global coverage is uneven, shaped by culture, infrastructure, illiteracy, the accidents of archival preservation, and the simple geographic fact that some events were better placed for observers in certain parts of the world than others. What would we miss if we applied the same scrutiny to our contemporary era? A supernova that appeared faint, red and low on the horizon in a direction where urban light pollution was severe. How long would it take for someone to notice? How long before the automated surveys caught it, before the professional observatories confirmed it, before the news escaped the astronomy community into wider attention? For a dramatic bright event in a clear region of the sky, the answer is probably hours. For a modest obscured event that showed up initially as a faint reddish star in a crowded field near the galactic plane, the answer might be days or weeks, and the cultural resonance might be far quieter than the historical record suggests. It should be. The people of 1054 knew their sky. They had no electric light, no entertainment competing for their attention at night, no screen between themselves and the darkness overhead. A new star was an event that inserted itself directly into their perceptual world with no mediation. Modern people, many living under skies so bright with artificial light that the Milky Way itself is invisible, might not notice the same object even if it appeared. The instruments would catch it. The announcement would go out on scientific channels. But the spontaneous universal recognition, the shared human experience of stepping outside and seeing the sky changed, might be muted in ways that make the modern era less observationally rich than it first appears. There is something important in this. The silence, since 1604, is partly a silence of the galaxy, and it is partly a silence of changed circumstances, changed skies, changed habits, changed relationships between human beings and the darkness overhead that for most of our history was the most reliable presence in our lives. The stars did not go anywhere. We moved away from them indoors into light. And yet the historical record also carries a more personal message, one that tends to emerge when you sit with these events long enough. SN 1006 was seen by a scholar in Cairo who wrote about it carefully, whose words survived, whose account we can still read and use to reconstruct the brightness of something that happened 1,000 years ago. SN 1054 was recorded by imperial astronomers who were doing their jobs, systematic, patient, professional, and their records became the thread by which modern astronomers found the Crab Nebula's age and origin. Tycho Brahe stood in the cold autumn air and asked passing peasants to confirm what he was seeing before he trusted his own eyes, and then spent 16 months measuring a dying star with more care than it had ever been measured before, and his measurements became the foundation of a philosophical revolution. Kepler watched a star that had been dead for 13,000 years and wrote about it with the full force of his considerable mind, and the event named after him is still one of the primary reference points in the study of Type Ia, supernovae 4 centuries later. Each of these people was doing the same thing, separated by centuries and cultures and languages and wildly different frameworks for understanding what they were seeing. They were paying attention. They were recording carefully. They were passing something forward. We are the ones who received what they passed. The remnants they watched are still there, still expanding, still teaching. The words they wrote are still legible. The thread of observation runs unbroken from a medieval scholar in Cairo to a satellite in Earth orbit, measuring X-ray emission from a 1,000-year-old shockwave. That thread is what science is. Not the accumulation of correct theories, though, that matters. The accumulation of careful attention passed carefully forward, generation by generation, so that each generation begins not in darkness, but at the edge of the light the previous generation managed to reach. The next supernova in the Milky Way, whenever it comes, will be received by people equipped with instruments that would have seemed magical to Tycho Brahe. It will be analyzed in ways and at wavelengths that Kepler could not have imagined. But the act at the center of it will be the same act that has always been at the center of astronomy. Someone will look up, they will see something that was not there before, and they will pay attention. That is the inheritance. That is what the historical record of galactic supernovae ultimately contains, not just data about stellar explosions, but evidence that looking up carefully and writing it down is one of the most consequential things a human being can do. There is a star in the shoulder of Orion that is not behaving the way stars are supposed to behave. It pulses. It sheds mass in violent eruptions. Its surface is not a smooth, stable sphere, but a roiling convective chaos of rising and falling gas cells, each one large enough to swallow entire planets churning through an atmosphere, so extended and diffuse that the boundary between star and space becomes a matter of definition rather than geometry. It varies in brightness unpredictably, sometimes dimming by half or more over months, sometimes surging back to its former brilliance, sometimes doing things that no stellar model fully anticipated. It is a red supergiant. It is one of the largest stars visible to the naked eye, and it is dying. Not tonight, almost certainly not tonight, but dying in the sense that matters astronomically. Its fuel is running low, its internal structure is evolving toward the configuration that ends in core collapse, and the clock that has been running since it formed from a molecular cloud, roughly 8 to 10 million years ago, is approaching on some timescale that neither we nor any instrument currently in existence can precisely determine its final hours. Betelgeuse. The name is a corruption of an Arabic phrase, most likely Yad al-Jawza, meaning the hand of Orion distorted through centuries of translation and mistranscription into something that sounds to modern ears cheerfully absurd for an object of such gravity. It sits roughly 700 light-years away, though the precise distance has been revised several times as measurement techniques improved and the uncertainty remains meaningful. At that distance, it is close enough to be one of the genuinely nearby red supergiant candidates in the Milky Way, close enough that a future supernova would create a display unlike anything seen in the modern era, close enough to be studied in unusual detail. And it is large in a way that resists ordinary comprehension. Place Betelgeuse where our Sun sits at the center of our solar system, and its surface would extend past the orbit of Mars. Some estimates push the outer atmosphere further still, depending on how one defines the edge of a star that does not really have one in the conventional sense. Earth would be deep inside it. Jupiter would be deep inside it. The distance from the Sun to Jupiter 5 times the distance from the Sun to Earth, more than 480 million miles, would not reach the surface. You would be inside the star in a region where the gas is so thin it barely qualifies as gas in any earthly sense, but inside it nonetheless. This is the scale of what is sitting in the shoulder of Orion every winter, visible to anyone who steps outside on a clear night. In the autumn of 2019, Betelgeuse began to dim. This was not unusual in itself. Betelgeuse is a variable star, and it dims and brightens regularly as part of several overlapping pulsation cycles, the longest of which runs roughly 400 days. Observers had seen it dim before, but this time the dimming continued past what any of the known cycles would predict. By December of 2019 and January of 2020, Betelgeuse had faded to roughly 40% of its normal brightness, the faintest it had been in the entire history of modern photometric measurement. It was visibly unmistakably dimmer to anyone who knew where to look, and the astronomy community, which always knows where to look, noticed immediately. The headlines that followed were predictable. Is Betelgeuse about to explode? Could we see a supernova this year? The answer, delivered cautiously by astronomers who understood both the excitement and the responsibility of public communication, was essentially probably not, but we are watching very carefully. They were right to be cautious. The great dimming of Betelgeuse, as it came to be known, turned out to have a more mundane explanation, though mundane is a relative term when applied to events on stellar scales. Evidence gathered in the years following the dimming, analyzed by multiple research teams, converged on a picture involving 2 compounding effects. The star had undergone a surface mass ejection, a localized eruption that threw a large quantity of material into the space around it. That material cooled as it traveled away from the star, forming a cloud of dust that intercepted some of the light traveling toward Earth and dimmed it from our perspective. Simultaneously, one of the star's natural pulsation cycles was in a cooling phase, reducing the surface temperature and contributing additional dimming. The 2 effects occurred together by coincidence, or by some coupling in the star's internal dynamics that is not yet fully understood, producing the dramatic combined result. Betelgeuse was not dying. It was coughing, loudly impressively in a way that generated terabytes of observational data and dozens of scientific papers and several breathless news cycles. But coughing, the episode was valuable for reasons beyond the immediate excitement. It demonstrated that Betelgeuse is capable of surface mass ejections of substantial scale, ejecting enough material to create an obscuring dust cloud visible from 700 light-years away. It confirmed that the star's behavior is genuinely complex and not fully described by existing models. It reminded astronomers that variability in a red supergiant is not a reliable predictor of imminent explosion. The star can do extraordinary things and still have significant time remaining before the final collapse. And it demonstrated with uncomfortable clarity how eager the public and the media are for a galactic supernova, and how carefully that eagerness needs to be managed against the reality of stellar timescales. When Betelgeuse does explode, and it will explode on some timescale estimated broadly at anywhere from a few thousand to perhaps 1,000,000 years, the event will be extraordinary. Current estimates suggest it could reach an apparent visual magnitude of somewhere between -6 and -12 at peak brightness. The midpoint of that range would make it roughly comparable to the full moon in brightness. It would be visible in daylight. It would cast shadows at night. It would dominate the winter sky for weeks, then months, fading slowly over the course of a year or more before finally dropping below naked eye visibility. It would also, in a quieter and more scientifically significant way, be detectable by neutrino observatories days or hours before the optical brightening, as the neutrino burst from the collapsing core travels outward through the star and into space. At 700 light-years, Betelgeuse is close enough that modern neutrino detectors, Super Kamiokande in Japan Ice Cube at the South Pole and others, would register thousands of neutrino interactions compared to the handful detected from SN 1987A in the Large Magellanic Cloud. The physics of core collapse would be laid open in a way no previous event has permitted. Orion would never look the same. The familiar figure of the winter sky, shoulders, belt, sword feet, would be permanently altered. One of its defining stars would become for months the brightest object in the night sky apart from the sun and the moon, and then it would fade, and in its place, astronomers would eventually resolve the expanding debris cloud and the collapsed remnant at its center. A new nebula, a new pulsar perhaps, a new object for future generations to study with future instruments. But probably not soon. That word again, soon, doing so much work while meaning so little in precise terms. Betelgeuse is famous. It is the star. People know the one that gets the headlines, the one whose name appears in popular science articles every time it does something unusual. But the list of plausible supernova candidates in the Milky Way extends well beyond Betelgeuse, and some of the less famous entries are in certain respects more instructive about the true nature of stellar evolution near its endpoint. Antares, the bright red star at the heart of Scorpius, its name meaning rival to Ares, rival to Mars in recognition of its reddish color and occasional brightness, is another red supergiant of comparable evolutionary stage. It sits roughly 550 light-years away, somewhat closer than Betelgeuse by most estimates, though the uncertainties in both distances overlap. Like Betelgeuse, it is large, luminous, and losing mass through a strong stellar wind. Like Betelgeuse, it is classified as a variable star, its brightness fluctuating over timescales of months to years. Like Betelgeuse, it is expected to end in core collapse on a timescale measured in astronomical time rather than human time, thousands to hundreds of thousands of years, with the uncertainty spanning that entire range. Antares is a binary system. It has a companion star, Antares B, a smaller blue-white star orbiting it at a distance of several hundred astronomical units. The presence of a companion does not dramatically alter the fate of the primary. In this case, the two are separated enough that mass transfer is not significant, but it adds complexity to the environment in which a future supernova would occur. and it provides astronomers with a useful reference star for studying the primary's variability and atmospheric properties. If Antares were to explode before Betelgeuse, a possibility given the genuine uncertainty in both timescales, it would produce a similarly spectacular display. The winter sky belongs to Orion. The summer sky for observers across much of the world belongs in part to Scorpius, and a supernova in Antares' position would blaze in the summer nights with a brilliance that would make the season unforgettable for anyone alive to witness it. But neither Antares nor Betelgeuse represents the full landscape of supernova candidacy in the galaxy. They are the visible faces of a much larger population. Consider the Wolf-Rayet stars. These are massive stars that have shed most or all of their outer hydrogen envelopes through fierce stellar winds or through mass transfer to binary companions. What remains is exposed the hotter, denser interior layers of the star burning brilliantly, losing mass at rates that would strip away the equivalent of the Sun's mass in less than 100,000 years. Wolf-Rayet stars are among the most luminous objects in the galaxy, some shining with the energy of hundreds of thousands of suns simultaneously. They are also, by stellar standards, extraordinarily short-lived. Their remaining lifespans are measured in hundreds of thousands of years at most, and for the most massive and most stripped among them, perhaps only tens of thousands. The Milky Way contains several hundred known Wolf-Rayet stars, and likely many more hidden behind the dust of the galactic plane. These stars are core collapse supernova candidates. In the most literal sense, they are massive enough, evolved enough, and stripped enough that the progression toward an iron core and subsequent collapse is well advanced. When they go, they may produce some of the most energetic core collapse supernovae in the galaxy, and under some conditions, if the collapsing core is spinning rapidly and the geometry is favorable, they may even produce gamma-ray bursts, the most energetic explosions known in the universe, beaming enormous quantities of energy in tight jets along the rotation axis. Gamma 2 Velorum in the southern sky is one of the closest known Wolf-Rayet systems, a binary containing a Wolf-Rayet star and a massive O-type companion, roughly 1100 light-years away. It is not an imminent supernova candidate in any practical sense, but it is close enough to study in exceptional detail, and it provides a window into the late evolutionary stages of stars that will eventually produce the kinds of core collapse events we are trying to understand. WR104 is a more dramatic case, a Wolf-Rayet binary system roughly 8000 light-years away, notable for the beautiful pinwheel nebula it produces as the stellar winds of its two massive components interact and spiral outward. It has attracted attention partly because of its orientation. The axis of the binary system appears to be pointing roughly toward Earth. If WR104 produces a gamma-ray burst, when its Wolf-Rayet component eventually collapses, the burst could be directed toward our planet. At 8000 light-years, this is not considered a serious threat to life on Earth. The intensity of the radiation reaching us would be insufficient to cause major biological harm, but it would be detectable, dramatically so. The white dwarf binary systems that produce type Ia supernovae present a different kind of candidacy, one that is harder to identify before the event and harder to place on any timeline at all. A white dwarf, steadily accreting mass from a companion, looks to ordinary observation like a moderately interesting binary system. The white dwarf itself is small and faint, too small and too faint for most surveys to study in detail at typical distances within the Milky Way. The mass transfer process produces some observable signals. The system may flare periodically as accumulated material undergoes surface thermonuclear burning in a nova event, briefly brightening before settling back to quiescence. But these nova outbursts, dramatic as they are not the final event. They are pressure releases. The white dwarf sheds some of the accreted material without reaching the critical threshold. The system resets and the accumulation begins again. T Coronii Borealis, TCRB, the Blaze Star, is perhaps the most discussed recurrent nova system in the current era. It underwent a dramatic outburst in 1866 and again in 1946. And in 2024, it showed pre-outburst behavior strikingly similar to what preceded the 1946 event, leading astronomers to predict an imminent nova outburst that would briefly make it one of the brightest stars in the sky. A nova event, not a supernova, and not the end of the white dwarf, but a surface explosion that would be dramatic enough for naked eye observers. The system is interesting not just for its immediate behavior, but for what it represents: a white dwarf in a close binary accreting mass, periodically erupting. Whether it will eventually reach the Chandrasekhar limit and detonate as a Type Ia supernova, or whether it will continue to shed mass in nova events and never quite cross the threshold, is not currently known. This is the fundamental difficulty with Type Ia candidacy. The process is slow, the signals are ambiguous, and the endpoint, the moment the white dwarf crosses from stability to catastrophe, arrives without the dramatic precursor behavior that makes red supergiants like Betelgeuse identifiable candidates. A white dwarf that detonates tomorrow would, in retrospect, have been identifiable as a candidate based on its binary configuration. But so would thousands of other white dwarf binary systems in the Milky Way that will never detonate, at least not on any timescale relevant to current human civilization. There is a deeper issue with all of this candidate watching, one that becomes clear when you step back from the individual stars and look at the statistical picture. The next supernova in the Milky Way may not come from any star currently on anyone's watch list. It may come from a massive star embedded in a dense molecular cloud in the inner spiral arms, a star that has not been catalogued as an individual object because the dust surrounding it prevents optical detection, a star that is going back through its final nuclear stages in obscurity, unknown to astronomer. It may come from a white dwarf binary system in the galactic bulge that appears in any catalogue currently compiled as an unremarkable point source among billions. It may come from a Wolf-Rayet star in a distant dusty region that has been catalogued but not studied in detail. It may come from a direction and a distance where, even if the explosion is intrinsically brilliant, the visible light never makes it through. The famous candidates Betelgeuse and Antares, the known Wolf-Rayet stars, are famous because they are nearby, because they are bright enough to study in detail, because their evolved state is obvious. But nearby, bright, and obviously evolved are selection effects. They describe the stars we know about, the ones we can see and study easily. They do not describe the full population of stars in the Milky Way that are approaching their ends. The galaxy contains an estimated 100 to 200 massive stars, within a few thousand light-years of the Sun, stars massive enough to eventually produce core collapse supernovae. Of these, we have detailed information about relatively few. The others are known statistically inferred from surveys mapped imprecisely through the dust. Any one of them could be further along in its evolution than the models suggest. Any one of them could be at this moment in the final stages of silicon burning hours or days in stellar terms from an iron core and subsequent collapse. We would not know, not until the neutrinos arrived. And this is where the timescale problem becomes most acute. When we say Betelgeuse could explode within 1,000,000 years, we are giving a range that spans the entire history of modern humans. When we say it could explode within a few thousand years, we are speaking of a period longer than recorded civilization. When astronomers occasionally speculate that it could in principle explode tonight, which is technically true, though not considered likely, they are acknowledging that stellar physics does not provide a precise countdown clock for any individual star. The uncertainty is not a failure of astronomy, it is a reflection of genuine physical complexity. The final stages of massive stellar evolution are governed by processes: convection in the oxygen and silicon burning shells, neutrino losses from the core mass loss through stellar winds that interact in ways that are computationally extremely demanding to model and observationally nearly impossible to measure directly in the stellar interior. We can observe a star's surface. We can measure its luminosity, its color, its variability, its spectrum. We cannot directly observe its core. We cannot watch the iron build up. We cannot see the moment the balance tips. What we can do, what modern astronomy has equipped us to do better than any previous generation, is listen for the announcement when it comes. Not wait for the visible light which may be hours behind. and may never arrive clearly if the star is obscured. But listen for the neutrinos, which carry the news directly from the core through any intervening material to instruments that are waiting underground right now. There is something philosophically satisfying and slightly vertiginous about this situation. We have a list of stars that might explode. We have instruments capable of detecting the event even if it is hidden from our eyes. We have a theoretical framework that tells us what should happen in what sequence, on what approximate timescale. We have historical records that tell us such events have happened before within our galaxy, within human historical memory, and we wait, not passively. Modern sky surveys monitor known variable stars, continuously tracking their brightness variations in search of behaviors that might indicate terminal instability. Infrared surveys scan the galactic plane for embedded sources that might be massive stars in late evolutionary stages. Radio observatories map expanding shells that might be recent or ongoing supernova events hidden behind dust. Neutrino detectors watch around the clock, sensitive enough that a galactic core collapse would register within seconds. But none of this watching controls the timing. None of it brings the event closer or pushes it further away. The stars follow physics, not calendars. They evolved on timescales that predate our civilization by millions of years, and they will reach their conclusions on timescales that the concept of urgency cannot touch. There is a version of this waiting that feels frustrating, the sense of standing at a window, watching a sky that should deliver something extraordinary and persistently declining to do so. And there is another version that feels different, more like the experience of sitting in a landscape that is changing on a scale you cannot directly perceive, knowing that the change is real, that the processes are active, that somewhere in the vast dark turning of the galaxy, stars are doing what stars have always done, building toward their endings with the patience of physics, indifferent to the watching. Betelgeuse will explode, Antares will explode, Wolf-Rayet stars scattered through the spiral arms will collapse, white dwarf binary systems will cross their thresholds and detonate. The machinery of stellar death is running everywhere in the Milky Way, at all times on timescales that dwarf human history. The question of when the next one becomes visible to us is a question of geometry, dust distance, and the accident of which star happens to be at the right stage, in the right location, at the right moment. That moment could be tomorrow. It could be 10,000 years from now. It could be right now, already happening. A core collapsing on the far side of the galaxy, neutrinos already streaming through everything, the light on its way, the news in transit, the announcement not yet arrived. We are, in the deepest sense, always already waiting. The message is always already sent. We are simply not yet at the moment of receiving it. And when we do receive it, when the detectors trigger, when the alerts go out, when the sky finally changes in the way it has not changed since Johannes Kepler stood in Prague and watched a star die, the experience of that moment will be shaped by everything we have built to receive it. Not just the instruments, the understanding, the centuries of accumulated knowledge about what supernovae are, how they happen, what they leave behind, what they mean for the chemistry of the galaxy, and the origin of the elements and the fate of stars. The next supernova in the Milky Way will be received by people who understand what they are seeing in a way that no previous generation could. That is the inheritance of 4 centuries of watching a quiet sky. Not the patience of waiting, the depth of preparation. Imagine a night like any other night, the kind of night that does not announce itself as significant. The sky is clear, or mostly clear. The temperature is whatever temperature it happens to be in whatever season you are in. Somewhere a dog is barking at something that does not matter. Somewhere a car moves through empty streets. The world is doing what the world does in the hours when most of its inhabitants have decided by a consensus no one organized to stop. And then deep underground, beneath a mountain in Japan, or beneath the ice of Antarctica, or beneath a lake in Canada, or beneath the Homestake mine in South Dakota, or beneath any of a dozen other sites where human beings have spent enormous effort and ingenuity building instruments designed to catch particles that pass through everything a detector registers something. Not one event, thousands of events, in seconds. Neutrinos arriving from a specific direction in the sky in a burst so concentrated and so intense that the statistical significance is immediate and unambiguous. The software that monitors the detectors running continuously, checking continuously, comparing every event against baseline rates, flags the anomaly before any human being is awake enough to notice it themselves. Alerts propagate automatically through the Supernova early warning system SNEWS to observatories around the world. Emails arrive, phones vibrate. Pages still used by some observatories for exactly this kind of urgent communication begin sounding in rooms where astronomers are sleeping. The message in its technical form is a set of coordinates and a timestamp and a statistical confidence value. In its human form, it is 4 words: a star has collapsed. The direction the neutrinos came from points to a region of the sky. Observatories with instruments already trained on the galactic plane begin examining the relevant field. Others slew the word astronomers use for the rapid reorientation of a telescope, a word that sounds almost violent and is to point toward the coordinates. Automated systems that monitor known variable stars in that region begin pulling archival data, comparing tonight's measurements against everything previously recorded. If the star that collapsed is known, if it is Betelgeuse or Antares or some other named massive star that has been on watch lists, the identification is almost immediate. The familiar point of light that was always in that position is gone, or changing, or already brightening in ways that no known variability pattern can explain. If the star is unknown, if it is an embedded, previously uncatalogued massive star in a dusty molecular cloud, the identification takes longer. The neutrino direction is not precise enough by itself to pinpoint a single star among the millions in the relevant field. Infrared observations begin, radio observations begin, X-ray satellites are redirected. The search is on for the source. Hours pass. In those hours, while most of the world sleeps, astronomy is having the most important night in living memory. Graduate students are being called. Senior scientists who retired years ago are sending emails to former colleagues. The International Astronomical Union is preparing circulars. Journals are clearing space. The machinery of scientific communication, normally measured in months from observation to publication, is preparing to compress itself into days. And the sky above has not yet visibly changed. The shockwave from the collapse is still traveling through the outer layers of the star. It will take hours, anywhere from a few hours to perhaps a day, depending on the size of the progenitor, to reach the stellar surface. Until it does, the optical brightening has not begun. The neutrinos escape from the core, immediately racing through the stellar envelope as though it were not there. The light is still trapped inside, fighting its way outward through billions of kilometers of stellar material that is simultaneously being torn apart from within. This is the interval, the gap between the neutrino announcement and the visible display that scientists have been anticipating for decades. The gap that SN 1987A in the Large Magellanic Cloud first made real when neutrino detectors in Japan and the United States registered a burst of events approximately 3 hours before the supernova became optically visible. 3 hours of knowing before the sky confirmed it. If the new event is a core collapse supernova close enough and favorably positioned, that gap will be filled with the most intense preparation in the history of observational astronomy. Every instrument that can be brought to bear on the relevant region will be brought to bear. Spectra will be taken of the field, establishing a baseline. Photometric monitors will be set to their most frequent cadence. Space telescopes will be contacted and their schedules reorganized. Scientists around the world will spend those hours doing what scientists always do when confronted with something unprecedented. They will argue carefully and productively about exactly what they are about to see and what it will tell. Foss them. Then the light arrives, not with a flash, not with the sudden appearance that the word explosion implies. From Earth, the optical brightening of a supernova is a gradual process. The shockwave reaches the stellar surface. The star's outer layers begin to expand and brighten, and over hours, and then days, a new point of light grows where before there was a familiar star or nothing obvious at all. But grow it does. Night by night, the new object brightens. The rate depends on the type of event, the distance, the degree of dust extinction along the line of sight, and the properties of the progenitor star. For a favorably located nearby event, the brightening might be dramatic and rapid. Within days, it might reach a brightness comparable to the brightest stars in the sky. Within weeks, it might rival Jupiter or Venus. In the most optimistic scenarios, a nearby low extinction core collapse or a Type Ia event in a clean region of the sky, it might reach a brightness that makes it visible in full daylight. At some point in this brightening, the event crosses a threshold. It becomes impossible to ignore, not just for astronomers with instruments and orbital assets and carefully planned observing programs, for everyone, for the person stepping outside to get the mail, for the child waiting for the school bus, for the driver glancing up at a traffic light, for the insomniac who happens to look out the window at 3 in the morning and sees where the familiar darkness should be. A new light sitting in the sky, with a confidence that admits no uncertainty about whether it belongs there. The sky has changed, and nothing the sky does, no aurora, no conjunction of planets, no lunar eclipse, prepares you for the experience of the sky changing in this particular way. Those events are anticipated. They appear in calendars and astronomy apps, and the plans of people who set alarms to see them. This is different. This is a change that was always possible, and never scheduled a disruption of the background against which every human life has ever been lived. A new permanent-seeming feature, added to the most stable visual environment our species has ever known. For a few moments, for the first few moments before the phones come out and the searching begins, before the need to understand and share and explain takes over, there might be something simpler. The experience of seeing the sky changed and not yet knowing why. The pure, unmediated confrontation with the unexpected. That experience does not last long in the modern world. Within minutes, the question of what is happening will be answered, not completely, not in the detail that science will eventually provide, but answered enough. A star exploded. A star in our galaxy. The light we are seeing left its source however many hundreds or thousands of years ago, and it has only now at this moment arrived. We are receiving news from the deep past, and the news is that a star has died, and the death is beautiful. In the weeks that follow, the supernova will be one of the most studied objects in the history of science. Every space telescope capable of observing it will be redirected toward it. The Hubble Space Telescope, or whatever its successor is by then, will take images at the highest available resolution. James Webb will observe in infrared, probing the dust and the cooling ejector. X-ray satellites will watch the shockwave heat the surrounding material. Radio arrays will track the expanding debris. Neutrino detectors will continue monitoring for secondary signals. Gravitational wave observatories will search for asymmetric collapse signatures. Spectra will be taken every hour, then every day, tracking the evolution of the expanding material. Each spectrum is a fingerprint of the explosion's chemistry, the elements produced in the nuclear, burning the velocities of the ejected material, the temperature of the photosphere as it cools and expands. By comparing these observations to theoretical models, physicists will test and refine their understanding of the explosion mechanism with a precision that no previous supernova has permitted. Papers will appear faster than they have ever appeared on any topic in astrophysics. Preprints will be posted within hours of observations being taken. Arguments will begin in the comment sections of those preprints. Conferences will be organized. Graduate students will build entire careers on the data from these weeks and months of observation. The event will define a generation of astronomy, the way SN 1987A defined the generation that preceded it, and in ways that SN 1987A, as instructive as it was, could not, because it occurred before the instruments we now possess existed. For the broader public, the experience will be something different. People will photograph it with their phones, and the photographs will be beautiful and slightly strange, a bright point in the daytime sky, or a blazing new star in the nighttime, one surrounded by the ordinary darkness it has interrupted. Children who see it will remember it for the rest of their lives, the way people who witnessed the 1994 Shoemaker-Levy 9 impact on Jupiter, or the 2017 total solar eclipse. Remember those events not as data, but as experiences that changed the texture of the sky for them permanently, that made the universe feel present in a new way. And teachers will have a gift. For a few weeks or months, the most abstract concepts in physics, stellar evolution, nuclear fusion, the life cycle of stars, the origin of the elements, we'll have an example anyone can point to simply by stepping outside. The iron in a blood cell, the calcium in a bone, the oxygen in the atmosphere, all of it traceable through the chain of stellar nucleosynthesis to events like the one visible overhead. The universe will have written its own lesson plan in the sky, and the lesson will be visible to anyone who looks up. But the supernova will fade. They always fade. The weeks of brightest display will give way to months of gradual dimming. The object that once competed with planets will decline to the brightness of ordinary stars, then of binocular targets, then of telescope objects. The world's attention, which attaches intensely to novelty and releases it when novelty becomes familiar, will move on. The news cycle will find other subjects. The social media posts will become less frequent. Most people will stop looking. Scientists will not stop looking. They will follow the event for years, for decades eventually, tracking the expanding debris, searching for the compact remnant at the center, watching as the shock wave sweeps up surrounding material and the remnant begins to glow at radio and X-ray wavelengths, mapping the spatial distribution of newly synthesized elements as the ejector cools and becomes transparent, gradually building the complete picture of what happened, not just the visible display, but the physics that produced it, the stellar life that preceded it, and the legacy it leaves behind for the interstellar medium it is expanding into. This is what happened with the Crab Nebula. Nearly 1,000 years after the 1054 supernova, astronomers are still publishing papers about it, still finding new things in its structure, still using the Crab pulsar as a laboratory for extreme physics, still learning from a death that people watched from their rooftops in the Song dynasty. The next galactic supernova will be the same. Whatever it produces, a neutron star, a pulsar, perhaps a black hole, that remnant will be studied for generations. The nebula it creates will be photographed and analyzed long after everyone alive today is gone. It will enter the permanent catalogue of the sky, the way the Crab Nebula has, and the Cassiopeia, a remnant has, and the remnant of Kepler's supernova has, as an object that contains, in its expanding structure and its chemistry and its energetic physics, the compressed memory of a single violent moment that human beings, in some cases, were lucky enough to witness. We have traveled a long way from the original question. We began with a silence 4 centuries of a galaxy that should have offered us a supernova and appeared not to. And we have found along the way that the silence is less what it seemed. The Milky Way is not quiet. It cannot be quiet. It contains too many stars in too many stages of evolution, burning through fuel at rates that guarantee catastrophic endings at regular intervals for the silence to be genuine. The rate is real. Several supernovae per century by the best available estimates. The events are happening. They are happening now, somewhere in the 200 to 400 billion stars of this galaxy, in the star-forming regions of the spiral arms, in the old stellar populations of the bulge, in the dusty, crowded lanes of the inner disk. What we lack is not the events. What we lack is the view. We live inside a dusty spiral galaxy, embedded in its plane, looking out through thousands of light years of material that absorbs and scatters the visible light we evolved to see. The most active regions of the galaxy, the ones most likely to host the supernovae we are waiting for, are the ones most thoroughly obscured from our position. The last 4 centuries of apparent quiet are at least in part an artifact of our location and our biology, the consequence of being creatures who can only see in one narrow slice of the electromagnetic spectrum, living inside a structure that places its most dramatic events behind its thickest curtains. G1, 9 plus 0.3 is there to remind us of this. A star that exploded within living memory, within the era of Edison and Darwin and Pasteur, whose death went almost entirely unwitnessed because the light was taken by dust before it could reach us. The galaxy was not quiet, the galaxy was hidden. Those are not the same thing. And the historical record tells us that when the geometry is favorable, when the dust is thin enough and the distance is short enough and the explosion is bright enough, humans notice. They have always noticed. From the scholar in medieval Cairo who described a new star bright enough to cast shadows to the imperial astronomers of the Song dynasty, who watched a guest star for 2 years, to Tycho Brahe, measuring positions in the cold Danish night, to Kepler, writing about a light that had been traveling for 13,000 years before it reached his eyes. Humans have always noticed when the sky changes dramatically enough to see. The next one will be noticed too, by instruments far more sensitive than human eyes, by detectors buried under mountains and Antarctic ice, by software watching millions of pixels of sky simultaneously, by a global community of scientists connected across continents and time, ophonis. And if the event is close enough, clear enough, bright enough by anyone who happens to look up at the right moment and sees a new light sitting in the sky that was not there the night before, what remains at the end of this journey is something quieter than the question we began with. We began with an absence. Why haven't we seen one? And we end with a presence. The presence of all the events we could not see, the dust-hidden deaths that scattered heavy elements into the interstellar medium without any human witness. The presence of the remnants, the Crab Nebula Cassiopeia, AG1, 9 plus 0.3 Kepler's shell, Tycho's expanding ring that testify to stellar deaths across the centuries. The presence of the candidates Betelgeuse in winter, Antares in summer Wolf-Rayet, stars scattered through the disk, white dwarf binaries accumulating mass in quiet binary systems, each one a clock running on a timescale we cannot read, precisely each one eventually destined to cross a threshold and announce itself, and the presence of something harder to name. The fact that we are here at all, that we are capable of asking this question, is itself the consequence of stellar death. The calcium in the bones that support your body as you read this was synthesized in a stellar core and scattered into space by a supernova explosion billions of years before the solar system formed. The iron in your blood, every red blood cell in your body contains iron atoms that were made in the interior of a massive star and released into the interstellar medium when that star died. The oxygen you are breathing right now, the carbon in every organic molecule in your body, the silicon in the rock beneath wherever you are standing, all of it has passed through the interior of at least one star, possibly several, forged in the nuclear fires we have been describing and distributed through the galaxy by the violence of their endings. You are in the most literal physical sense made of supernova, not metaphorically, not poetically. The atoms of your body have a history that includes stellar interiors and stellar explosions, molecular clouds and planetary formation, billions of years of chemistry and geology and biology arriving finally at this moment. You are the galaxy looking at itself. You are matter that became complex enough to wonder where it came from. That is not a small thing. That is perhaps the most extraordinary fact about the silence we have been examining. The galaxy has not been quiet because it was waiting. It has been working, producing elements, scattering them, building complexity across billions of years of stellar birth and death. Each generation of stars, enriching the interstellar medium with heavier elements, making possible the next generation of stars and planets, and eventually the kind of chemistry that produces creatures capable of looking up and noticing the silence and asking what it means. The silence is not emptiness. It is the pause between one announcement and the next in a conversation that has been ongoing for 10 billion years and will continue long after the sun itself has exhausted its fuel and returned its matter to the galaxy that made it. Somewhere in the Milky Way right now, a star is in its final stages. Its silicon is burning. Its iron core is growing. Gravity is pressing inward with a patience that has been building since the moment the star was born. The end is close, close in the only sense that matters, which is not days or years or centuries by human reckoning, but close in the sense that the long arc of stellar evolution has nearly reached its conclusion, that the negotiation between gravity and nuclear fire is approaching its final terms. When the collapse comes, neutrinos will stream outward from the core at close to the speed of light. They will pass through the star in seconds. They will cross whatever distance lies between that star and Earth, without stopping, without slowing, without noticing any of the dust or gas or stellar systems they move through. They will arrive here perhaps in a few years, perhaps in a few thousand years, perhaps tomorrow, and if our detectors are still running, if someone remembered to keep the instruments maintained and the computers online and the monitoring software updated, those detectors will register the arrival. And then, hours later, As the shockwave reaches the stellar surface and the star's outer layers begin their explosive outward journey, the light will follow. It may fight through dust. It may arrive here reddened and dimmed. It may arrive too faint to see with the naked eye, or it may arrive brilliant enough to read by. We do not know which, because we do not know which star it will be, or where that star is sitting relative to the dust lanes and the clear windows and the geometry of the galaxy. But the light will come. It always comes eventually from everything that burns. There is a star somewhere in this galaxy whose light is already traveling toward us. It left its source long ago, perhaps centuries ago, perhaps millennia, and it is moving at the only speed available to it, crossing the dark between the stars in a straight line toward the small rocky planet where, for a brief and improbable moment in the history of the universe, creatures evolved who could look up and recognize it for what it was. Not a new star. A death. A death so old it happened before anyone now alive was born. The news traveling across the dark for longer than many civilizations have existed, arriving at last in a sky that has learned slowly and with great effort to receive it. The light is already on its way. We are simply not yet at the moment of its arrival. And when it comes, when the sky finally changes, when the new light appears where no light was before, we will look up. We will recognize it. We will understand in ways that no previous generation could fully understand what we are seeing. A star lived. For millions of years it burned and changed and built complexity in its interior and scattered that complexity into space. And at the end, in the smallest fraction of a second, relative to the whole long arc of its existence, it gave everything it had left, all the energy of its collapse, all the forged elements of its interior, all the neutrinos from its dying core, outward into the galaxy that made it. The light from that gift is coming toward us right now, through the dark, through the dust, through the long silence between one announcement and the next. It is almost here.